Hello everyone. I would like to thank the organizers of Strings 2025 for giving me the wonderful opportunity to present my work. So we have been working on partition functions and phases of quantum field theories in AdS spaces. So here is my poster, which I will now describe briefly through the following slides. The main motivation behind our research has been that AdS acts as an IR regulator and changes the IR behavior of QFTs from flat space, and these changes are captured by what is known as the effective potential. To find the effective potential, there are various perturbative methods available which involve computing one-loop determinants. So our research has been divided into two parts. We have first given a method to compute one-loop partition functions for scalars, fermions, and U1 vectors in Euclidean as well as thermal AdS. This has been done by finding the eigenfunctions of the corresponding differential operators in Euclidean AdS and then generalizing these eigenfunctions to obey the periodicities of thermal AdS. And then we use these results to study phases of different QFTs in AdS spaces, both Euclidean as well as thermal AdS. So there are some methods already known to find these partition functions. We have given a new method which uses the spectral form of the propagator and very nicely amalgamates both zero and finite temperature calculations. So the basic setup involves writing the effective potential in terms of, say, the fermionic and the bosonic partition functions. For example, for a theory like the Yukawa theory, or for example, for scalar QED, we can write this in terms of the gauge, the ghost, and the scalar determinants. The idea then is to find the log of the traces by integrating the following expressions. This can be done once we know the solutions for the corresponding differential operators. For example, for the scalars, we have the following solution. These solutions are then generalized for thermal AdS and are written here. Once we have these solutions, we can do the trace computations to give following results. For example, these are the results at zero temperature. These are the results at finite temperature, the partition functions. At even and odd d, the scalar fields, the fermions, and the vectors. Once we have these results, we continue by first regularizing the volume of thermal AdS, since this is divergent, and then studying phases of different theories in AdS. For example, one major finding of ours in AdS2 was the existence of symmetry breaking phase, which in contrast to flat space occurs in AdS. Also, we get a region where both the symmetry breaking and symmetry phase preserving phases coexist. The next story we have is of the Gauss-Navier model. So for example, here the discrete chiral symmetry, which is restored at high temperatures in flat space, remains broken at all temperatures in AdS3. We also studied the U1 vectors, the scalar QED theory, where we could retrieve the flat space Coleman line potential for AdS4, and also we got the following finite temperature phase plot. So we have studied various different theories in AdS and observed quite a few differences in flat space after having computed the one-loop determinants. So I look forward to discussions on the poster. Thank you.